dear students, let's move on. In today's lecture, we will derive the expression for the effective mass. We will consult two books. One is this one, which is the book by Kittel, 8th edition, and the other book is the book written by Levi, whose pages I have already sent to you. So we will go on. Now, what is the effective mass? You know that when the electron is in just one atom, or when the electron is free, its mass is called the its mass is called the normal mass of the electron. But once this atom becomes the part of a solid, and this atom is being interacted with so many other forces, it's a sort of tense in the solid, so the electron do not behave as a free electron. Its mass changes, and this mass is called the effective mass. The effective mass also depends on the location of the electron, whether this electron is in the valence band and at which level of the valence band. Similarly, if this electron is in the conduction band and at which level of the conduction band, it depends. The effective mass depends on its location. You can say that the effective mass depends on the band edge, the valence band edge and the conduction band edge, and these band edges are of different shapes for different solids. So it means the effective mass is not constant. It depends on the location, and it depends on the curvature of the band edges. So that's we are going to get today. So let me go through the description given over here from Kittel. So when we look at the energy wave vector relationship, and this is the energy wave vector relationship for the free electron. For free electrons, we see that the coefficient of k square determines the curvature of epsilon vectors versus k. Turned about, we can say that 1 over m, the reciprocal mass, determines the curvature for electrons in a band. There can be regions of unusually high curvature near the band gap at the zone boundary, as we see from the solutions in the chapter number 7 of the wave equation near the zone boundary. If the energy gap is small in comparison with the free electron energy at the boundary, the curvature is enhanced by the factor lambda over Eg. In semiconductors, the bandwidth, which is like the free electron energy, is of the order of 20 electron volts, while the band gap is of the order of 0.2 to 2 electron volts. Thus, the reciprocal mass is enhanced by a factor of 10 to 100, and the effective mass is reduced to 0.1 to 0.01 of the free electron mass. So you see how much the effective mass changes from the free electron mass. These values apply near the band gap. As we go away from the gap, the curvature and the masses are likely to approach those of the free electrons. To summarize, the solutions of chapter 7 for U positive, an electron near the lower edge of the second band has an energy that may be written given by this equation. Here ME is the effective mass and M is the free electron mass. So here K is the wave vector measured from the zone boundary, and ME denotes the effective mass of the electron near the edge of the second band. An electron near the top of the first band has the energy given by these equations. Equation number 25. The curvature and hence the mass will be negative near the top of the first band, because the curvature over here is negative. So this is how you can understand the reason we pointed out, the point we discussed in one of the previous chapters, that the effective mass can even be negative. But we have introduced a minus sign into equation 25 in order that the symbol mh for the whole mass will have a positive value. Okay, so we will go through, you can go through the rest of these pages and see that this is the final expression we will derive for the effective mass of the electron, equation number 28. So this equation is 1 over m star equals to 1 over h cut square, second derivative of epsilon versus k curve. So this is the curvature, in fact, the curvature of the band edges. So we see that the effective mass is very much dependent on the curvature. Now to derive this expression, I would suggest that you should consult the other book. Let me show you the book, the pages from Levi. Okay, here you can take up this topic, the effective mass, and you can go through and see that, let me okay, this is a bit small, but I want to make it, focus it to a larger size. Anyway, so this is the group velocity, the expression for the group velocity, equation 8.16. You know that group velocity is the derivative of frequency with respect to k, and this is the expression for the energy, which is equal to h cut omega. So when you combine these two equations, you get the group velocity given by this expression, and we have this equation, derivative of E with respect to k is equal to hvg. Okay, thus as we stated earlier, the slope of the energy wave vector curve, dispersion curve, is proportional to the group velocity. If the electron is in an electric field, the change in the energy of the electron due to the work done on the electron would be equal to this. So dW is equal to EH into dx, that is, the work done is equal to force, which is EE into dx, which is the distance, and this is equal to EE Vg into dt, because the displacement or distance is equal to the velocity into time. However, this change in energy can be expressed as this as well. So here we have written the differential of energy, and since E is a function of k, so we have dE over dk is equal to hvg into dk. So dE is equal to hvg dk, and hvg dk is equal to E into vg into dt, and dk comes out to be this, and we get the equation 8.17, and so now we come to the acceleration. You know that acceleration is the derivative of the group velocity here. So when we substitute the value of the group velocity, we get this expression, and moving on further in straightforward steps, you can come to the equation of the energy, and then the equation of the effective mass, here written as equation 8.18. So this is the equation for the effective mass, m star is equal to h square over the second derivative of energy versus k. This is the same equation I told you from Kittel that we wanted to derive. Kittel has also derived this, but in a very fewer steps, but here you can find this derivation in more detail. So that's why we have consulted this book. So go through these pages from 331 to 337. Here at page 336, the negative effective mass and the holes is discussed, that why the effective mass is negative for the holes, and here there is an explanation given that if you can consult this diagram, figure 8.10 demonstrates how m star may be smaller than m or even negative near a Brillouin zone boundary. In the figure A, the energy of the electron beam incident on a crystal is slightly too low or too high to satisfy the condition for Bragg reflection, and the beam is thus transmitted through the crystal. So there is no absorption because the energy is slightly less or greater than the energy required for absorption. Okay, in the figure B, the application of a small accelerating or decelerating voltage across the grid, this is the grid, so if we apply a small voltage that can make up this difference if the energy of the incident photon is less or greater, then that can be adjusted by the voltage applied to this grid, and we will have a small change in the energy of the beam produces a large change in the momentum, because as soon as the energy matches we will have a reflection. So it means there is a large change in momentum, because before incidence the electron was moving in this direction, the photon was moving in this direction, and after absorption, after this reflection, it just changes its direction, so there is a large change in the momentum. So what is being said here, that is a small change in the voltage applied here, you get a large change in the momentum, so that leads to the negative effective mass. So go through these pages for the negative effective mass, and you must go through the pages 331 to 337 from Levi, and also pages as mentioned from Kittel. So that will make up your today's lecture, and we will in fact that is the end of this chapter on semiconductors. No, sorry, it's not the end. We have few other topics to be covered, but that is all about today's lecture. So go through the pages mentioned, and we will have discussion during the lecture. Okay, thank you very much.